Hello, everyone. Also happy to be here. My name is Alec Dyer. I'm a current graduate student in geography, and I'm working with Andres. And I was actually supposed to have a poster, and on Thursday a spot opened up, and now I find myself here, and I had to create a presentation over the weekend. So, life as a graduate student, right? Thank you. So a lot of this stuff is going to be very preliminary, but I'm hoping to draw out some really interesting trends and things to look at for the future. And specifically, delayed mortality, I'm kind of working off the ideas that Matt just presented, but focusing on the Labor Day fires and how delayed mortality might be currently happening there. So we have the whole story of delayed mortality, and it decreases the amount of fire refugia and gonna have over time limit forestry generation, also have influence spot owls and all that. Try not to repeat stuff too much. But the questions we can ask about what's going on at the Labor Day fire specifically, is it happening? If so, to what degree, where, and when? So I wanted to set the scene a little bit. Looking at the 5 mega fires that happened during the Labor Day fires in the Western Cascades. And if we want to look at, say, the kind of pre-fire drought before it happened, this is a plot by Riley et al. 2020. And you can see that in the top part of the graph is the EDDI, Evaporative Demand Drought Index, that measures measures moisture at the atmospheric surface level. So we can see that there's a lot of dry conditions, especially 1 week prior to the fire that's on the right side. And then we look on the bottom, we have the energy release component, which is about the fuel aridity. And while pretty dry, especially right before, at the lower end of it, where that Archie Creek fire is especially dry and lots of dry fuels to burn. We can all look at this temporally, and what you all know today, that these fires are mainly driven by easterly winds and arid conditions, with the first part of the fire happening with both wind and aridity, and the second part with aridity only. And one interesting fact about this fire that maybe differ from other fires in the past is that this heat dome happened in 2001 after the fire. It was about from late January to mid-July, and it had really high above average temperatures around here in the Western Cascades specifically. And I think that actually this heat dome might have a really big effect on delayed mortality, and that's something I want to look at in this research. So my first research goal is to quantify the spatial and temporal trends of delayed mortality using some maybe to high resolution, probably just mid-resolution satellite imagery with validation data to do that. And I'm estimating delayed mortality with RDMBR. However, I'm adjusting this original formula to account for just delayed mortality by looking at instead of the pre-fire MBR, the immediate MBR, and then seeing how that MBR changes over time, just like MAP. So if I make a little graph that's more specifically about the Labor Day fires and how I'm calculating delayed mortality, I'm also looking for the minimum MBR after the immediate portion of the fire. And here I'm actually calculating the immediate portion of the fire at October 2020. And that's because if I say the immediate burn severity is the next summer in June, July, there could be some delayed mortality occurring from that fire that won't be captured separately from the immediate mortality. So by adjusting where the immediate burn severity time frame is, we can hopefully see some trends in delayed mortality, and the heat dome might be one of those trends that we find. Boom, heat dome, right around there. And this is kind of a spiel that goes through the rest of how I'm calculating it with mean composite and looking at the minimum. And also, I have a little question mark up there saying that I think that we're going to need some different thresholds in order to calculate or say group burn severity into some kind of thresholds of like low, medium to high that we'll need validation data to do so. And so if I look at some of these maps, on the left column, I'm showing the immediate burn severity, and I'm actually using the same thresholds that Matt Riley found in 2017 for the Western Cascades. And there's something very different about these burn severities on the left side versus what we've seen today. I'm not actually capturing a lot of really high severity classes in this. And I think that's because of my time frame that I look at from actually here October to December, because I wanted some more imagery to look at. And that's very different. And so perhaps we're seeing a lot of that really high severity in the fires in all these other photos because that heat dome effect has potentially had an influence on that. And then we could also look at the delayed mortality, and that's shown in the red, so the more red, the more potential delayed mortality. And like Matt found, it's also very clustered, and from these maps, it looks very significant. However, this is still preliminary, so more detail and research is needed to back these up. And I also want to mention that I removed any salvage logging that happened post-fire. And if you want to learn more about that, go see the poster by Aaron and Matt after this. And so I want to just kind of go over some exploratory statistics of the data that I've grabbed. And before that, I had to do a bunch of filtering, and I kind of want to bore you too much, but taking out the salvage logging, taking out any roads or water. I'm also looking at, I don't want any pixels that had a major disturbance after 2016, but prior to the fire, because I'm looking at some GNN data that was from 2017. And then I'm also seeing a lot of really big outliers so far in my RD-MBR values for immediate and delayed. And so I wanted to clip those for the sake of this talk, and that's something I'll need to look into later. And I'm also just focusing on some potential vegetation zones that we might be interested in. And with a grain of salt, my results. But first, some theory. If we think about our immediate post-fire RD-MBR values, so that's like your, whatever you say, like your right after the fire, that's your burn severity values, or RD-MBR values. And as time progresses, if it moves to the left, as shown in green, we'd say that's recovery, because the change in RD-MBR is lower, or change in MBR is lower. But if it goes to the right, we're actually seeing a potential more decline. So more tree mortality, or may not necessarily tree mortality, but more injury. Trees are declining in their health. If that original curve starts going down and becomes more wide, delayed mortality could be happening more randomly at maybe some areas more, some areas less. And if it gets maybe shifted and squished, delayed mortality is likely happening at a specific, say, burn severity. Maybe it's moderate, maybe it's high. And so these are the RD-MBR values that I've found so far, with the immediate in black, and then the delayed mortality in 2021 in green, and delayed mortality in 2002 in blue. And we do see a bit of a shift to the right, indicating that delayed mortality is occurring in these plots. And if we make some plots of immediate RD-MBR on the x-axis and delayed RD-MBR on the y-axis, 2021 is on the top, 2022 is on the bottom, we see a pretty linear trend between those two. And so we can kind of hypothesize that, and from what we understand in past literature, that delayed mortality is really a function of the immediate mortality, how much burn happened originally. We can also look at RD-MBR values by burn severity. I actually see, like I mentioned, I don't have a lot of values in the high burn severity range. And if we break it up into the delayed 2021 and delayed 2022 again, we can see some interesting trends where for the delayed mortality in 2021, they're all above 0, so delayed mortality is occurring in either of the group. But if you move to 2022, the high burn severity RD-MBR values drop pretty significantly to a median around 0. So that could be telling us that we can hypothesize that for delayed mortality for a high burn severity, the trees are likely to die within the first year. We can also ask some questions about where mortality is occurring. This is just elevation by burn severity group. And we can see that kind of unlike what we can expect, for the highest burn severity group, we have most of that happening in low elevations, but what we kind of would expect to see in higher elevations, more cooler mesic forests, that they may be fire prone, so fires are more likely to happen around there. And if we look at slope, it kind of just follows our understanding of normal fire mechanics, where high slope equals high burn severity. If we're looking at cover class, in the low burn severity, There's not a lot of difference between the closed, moderate, open, and sparse cover classes, but low severity, I think I said. But in the moderate burn severity, the closed and moderate cover classes are actually showing higher delayed RD/MBR values in 2021. So, and if we look at 2022, we also see higher RD/MBR values in the moderate burn severity in the middle for those colors in red and yellow. And so I think that this might be due to increased competition for resources within these closed canopies. If trees are close together, they might be injured by fire, and not enough resources or not enough to let them all survive, and only a few do. Or it could be a factor of just high burn severity through the canopies there. And then we can also look at how forest structure influences delayed mortality. There's not much, so we're looking at this is looking at the density of trees. And if we look at some of the delayed values again, in the moderate, we see some trends towards positive. Very slightly, the data is very variant, which needs to be fixed, absolutely. But if there is that positive trend, so as the density of trees increase, you have more delayed mortality. That just kind of talks about more of that competition that I mentioned. And I think this is not the last one, but stand age. We don't see a lot of high burn severity in old trees. So most of the high burn severity is in the lower age trees, which we expect. Those thin, young stands, they just burn really high severity. And if we look at that versus delayed, these are actually flipped, my bad. 2022 is now on top, 2021 is on the bottom. But we see a pretty linear trend, especially in the low and moderate severity classes, with age on the x-axis and delayed mortality on the y-axis. So as the age of trees get older, there's more delayed mortality there potentially. And we think that this just could be because it's likely for the younger trees to die immediately, and so they don't have the chance for delayed mortality, like they're already dead. So might just only see delayed mortality happening in those older growth forests. And lastly, how did the heat dome influence delayed mortality? Well, I was working very hard to try to get some interesting trends here over the weekend, but unfortunately it is still a question mark to me. And I look forward to doing this more, and if anyone has any ideas and wants to talk more about this, I'm super happy to do so. Some of my hypotheses, though, include that trees that are in a high-density, closed forest will experience more delayed mortality as a result of the heat dome, just because of that increased competition for water and other resources. And then also taller trees will be influenced more by the heat dome. They're already probably potentially hurt from the fire, and so their ability to suck water up from the ground, the taller they get, is more difficult. So those also might be more prone to delayed mortality. And one of the important part of this this project is to make sure that we are validating this data, and I'm going to be doing that with FIA plot data that Jeremy Freed and Sebastian Busby talked about earlier, and that they have about over 200 plots available that were remeasured right after 1 year after the fire, and hopefully I can get some more years afterwards. That'd be a good necessary to do this. And also, like Matt was talking earlier, I can also use some really high-resolution imagery for some validation, such as the PlanScope imagery at 3 meters, or maybe even that NAPE imagery at 1 meter. And I want to do this at multiple scales, so looking at Landsat, the pixels are at 30 meters, and then at Sentinel, which it can range from 10 to 20. So looking at how maybe this happens at the stand level versus the landscape level. And the second part of this project is looking at the drivers. Why is delayed mortality happening? And maybe with those exploratory statistics that can help me understand why. But I wanted to create a boosted regression tree model in order to tee out some of those more maybe nonlinear relationships. And some of the proposed drivers, they can be broken up into direct and indirect drivers. So a direct driver would be really just like the fire effects, the amount, like maybe the amount level of burn severity, and that maybe their cambium necrosis happens, so they're no longer able to survive. And then there's also those indirect factors that I talked a little bit earlier, potentially competition, the heat dome, and really I want to throw the kitchen sink at this and see what comes out. Boosted regression tree models are great because they are non-parametric, they do not care about the distribution of your data. They can identify nonlinear relationships, and they're pretty fast. And I just want to end with maybe not some major conclusions, but some thoughts about the future work and expectations of this project. And so we're going to need to validate these observations. Okay, and I'll go through this quickly. But I think the most important part is thinking about the heat dome and specifically think about if we're using MTBS that looks at a year later to look at what the immediate mortality is, that might not be the case of how to do this because of that heat dome, and that might be something really interesting to look at. So stay tuned. I'm happy to talk more if you have any ideas about that, and thank you.